Okay, Zita, take it away.
Hi, everyone. Thank you so much for coming. I'm really excited for being here. And I was planning on having this workshop in a more like casual, informal manner. So whenever you have a question, just don't hesitate to unmute yourselves and then just ask that question. And every now and then, of course, I will be also checking the chat. But if you want to, just to ask something right away, just unmute yourself, please. Okay, so I'm going to share my screen. Now my question is, do you see like one large slide with the title of the presentation? Okay, so it was a successful sharing. So let's get to it. So today I would like to give you, in a way, an introduction and the practical exposure to Bayesian data analysis, with special attention to some questions that I think it can address really well that come up often in health sciences, or could be useful in a way, like how in a way Bayesian methods could be useful for health scientists, and how this free open source user-friendly software JASP can actually facilitate the analysis, or like actually using these methods. So I wanted to start with the general question of like, why would you want to do that? Why would you want to become a Bayesian and do Bayesian data analysis? And one thing that I would like to emphasize is that one thing that only Bayesian statistics can do is to integrate, in a way, prior knowledge in a principled way into the data analysis. And in health sciences, we often have like a wealth of prior knowledge available, for example, about the disease or condition being studied, or effectiveness of different interventions or treatments. And really, like Bayesian data analysis provides a principled way to include that into the analysis, and this way improve the accuracy or precision of the estimates. Now, another thing that I would like to focus on today is that Bayesian data analysis really provides a natural and principled, intuitive way of handling uncertainty. And it does that with probabilistic inference. So you can actually make probabilistic statements about model parameters, about hypotheses at the end of your analysis. So every Bayesian parameter estimate would come with a probability distribution, which allows researchers to quantify uncertainty surrounding the estimates, or even surrounding person-specific estimates. So you are able to, for example, have personalized posterior probabilities of certain risks if you fit Bayesian models. So it's very intuitive, very easily interpretable, and there are many ways that the Bayesian framework can just facilitate, in a way, also propagating uncertainty through your modeling. So you can have like flexible ways of including a measurement model or a missing data model as part of your larger model on regression or longitudinal data analysis. Today, we will be focusing on hypothesis testing a lot, and I want to talk about how, in a way, the Bayesian approach is more realistic and more useful for testing hypotheses. And one thing that I really want to emphasize, that with this approach, we can actually quantify evidence for a null hypothesis. So we can say something about null effects. For example, we can say something about an absence of a link, or like something being zero, as opposed to the more classical methods where we can only reject or fail to reject the null hypothesis. So, for example, if you have a bad side effect, usually from an old treatment, but your new treatment would not have that, then how could you quantify evidence for the absence of that relationship? Or what aggravates or what would not aggravate an undesirable behavior? And especially in the era of big data, when we are measuring, when we have the opportunity to measure a lot of things in terms of variable selection, and all these methods can be really useful. Now, another thing that I want to show you today is how we can actually also do intermediate analysis without losing power in the Bayesian framework, how we can sequentially update our inferences in the Bayesian framework. And one thing that I'm not going to focus on today, but I wanted to mention here is that there are lots of computational algorithms in the Bayesian framework that work with Bayesian inference, but they are not developed for likelihood or frequencies-based inference. And they usually make it possible to fit very complex model that might be impossible to fit with traditional methods. So it really helps you with the implementation of complex models. In fact, one of the famous Bayesian statisticians, Andrew Gammon, said that most of the classical statistical tools, have a Bayesian version too, and the Bayesian version will usually make things better. So even if you don't want a very complex model, but just your regular model, fitting it in the Bayesian framework will still benefit you. Okay, so I wanted to first talk a little bit about how the two different frameworks, the frequentist and the Bayesian, conceptualize probability, because that's in a way the big difference between the two that actually leads to differences in inference as well. So in the frequentist framework, probability is really seen as a limiting frequency. So you're thinking about it as relative frequency in the long run with infinitely many samples. So you have these kind of assumptions, and the uncertainty that you get, for example, around your parameter estimate is really due to the randomness of the observed data. So if you look at the figure here, like you can see that your model parameters have one true value, and there is, for example, an error interval around it. But in any case, you cannot assign probabilities to these model parameters. You just have some error around them. And this error is due to randomness in the observed data. In the Bayesian framework, uncertainty or probability is also due to the lack of knowledge on the parameters. And we can actually assign probability densities, probability distributions to the parameters, as you can see here in this picture. And the main advantage of that is really that you can assign probabilities to any event you want. So you don't need to be limited to those events that are actually repeatable. So probability is more like a degree of a belief about an event in the Bayesian framework. And this different conceptualization of the probability also leads to difference in inference. Like in the frequentist framework, your inference is on the sample space of the different outcomes, and in the Bayesian framework, it's on the parameter space. Or in the frequentist framework, you condition on the different intentions, on the different sampling plans. While in the Bayesian framework, as you will see, we are conditioning on prior knowledge or information about the model parameters. So here is just a quick representation of how Bayesian inference proceeds in a nutshell. So in a Bayesian inference, all we do is that we express our uncertainty or degree of belief. We quantify this by probability, and then we rely on Bayes' rule to update our current state of knowledge with information that we generally gain from the data. So we have some prior uncertainty, prior knowledge, and it's updated by means of the data to yield something we call posterior uncertainty. So we go from cause to consequence, we do deduction, or from consequence to cause, as you can see here, doing induction. So hypotheses that predict the data well receive a boost in credibility, whereas hypotheses that predict the data poorly will suffer in a decline. So in a way, data generating processes, you can think about it more generally, that predicted the data relatively well will become more credible in Bayesian inference. And the opposite is true too, that data generating processes that don't predict the data well, they predict them poorly, they will become less credible. And practically, this is always what we do. We have like some prior beliefs, prior knowledge, we learn from the data, we update it, and we have some posterior state of knowledge. If you get the gist of it, it's in a way, it's almost boring because it's always the same kind of Bayesian arm you turn when you do Bayesian inference. But this is really the gist of it. It's always the same cycle in a way. So now I just want to go more into the Bayesian principles, the basic concepts, and cover those that we are all on the same page before we actually get into some more practical hypothesis testing or some exercises that I was planning for this workshop. So let's start with some history. So Bayes' rule is actually very old. Thomas Bayes, who wrote it down, lived from 1702 to 1761. And actually his work was published posthumous. It's Essays Towards Solving a Problem in the Doctrines of Chances. He was a British Presbyterian minister, but his hobby was mathematics. And I mean, at that age, people did not really develop these methods, or they didn't really care about probability to, help health science research, for example, but it was more about gambling and how to get better at that, how to maximize the outcome of that. But while Bayes was the one who described Bayes' rule and all, it was really the French mathematician Pierre-Simon Laplace who should be credited for Bayes' theorem, because he was the one who worked out the formula, the method, the utilization, and also he did a lot in a way for Bayesian inference or Bayesian statistics. And then later it was really Harold Jeffreys, who you see from 1891 till 1989, a British geophysicist who revived Bayesianism and laid down the foundations of Bayesian statistics in his book, Theory of Probability. So let's see Bayes' rule. You might be familiar from your stats classes about Bayes' rule for observable random variables. So when you consider the conditional probability of an event A given event B, this is the conditional probability, and we know that this is not equal to the probability of event B given event A, because that would be the conditional probability fallacy, the fallacy of the inverse. And a good way to remember that actually comes from Bayesian researchers, Ott and DNS, who said that the probability of being dead, given that a shark has bitten once, had clean off. So probability of death given shark bite is 1, but the probability that the shark has bitten once, had clean off, given that one is dead. So the opposite of the probability is actually very close to 0. So because most people die of natural causes, of course. So just a good way to remember that when you have a conditional probability, you do have to use Bayes' rule to actually able to calculate this conditional probability. So this is really useful and it's widely applied, of course. And what we do in Bayesian statistics is that we do not only apply it for observable random variables, so to events, but we can also apply it to parameters or models or hypotheses. So I'm switching out A here with theta to denote parameters, and B here with the data, Y. And you can see that the rest of the formula just proceeds the same way. And I'm going to explain now the different parts of the formula. So this is what we call the posterior distribution. This is really the focus of Bayesian inference, is the distribution of the model parameter or parameters theta given the data. This is always what we get at the end of some Bayesian data analysis. And it equals to the prior distribution multiplied by the likelihood function and divided by the marginal likelihood. But let's see, so this is the prior distribution of the parameters. This represents our beliefs or knowledge about the probability of the different values for theta before observing the data Y. This here is the likelihood function. The likelihood function of the data is a function of the unknown parameters. What's interesting here is that the data are fixed here, in fact, and the parameters are random. So it's like really the opposite of the frequentist inference. So we call it a likelihood. So this is not a probability density function per se. And these, the prior and the likelihood multiplied together is divided by the normalizing constant, that in a way makes sure that the posterior probability will integrate to 1. So it's And this could be like a sum or an integral, depending on what kind, depending on whether we have continuous or discrete variables. And very often this normalizing, we actually don't need to do parameter estimation. And I will just explain this in a moment. So let's see just some examples of how the prior and the likelihood work together to get us to the posterior state of knowledge. So if you have a prior state of knowledge that we would often call uninformative, so for example, assigning equal probabilities on a range of parameter values. So let's say we have a parameter that can only take values between 0 and 1. This is a uniform distribution for the prior on that parameter. That would be uninformative because it's assigning equal weights to all parameter values. Now we gain some information from the data. And you can see that here I'm plotting the likelihood function value. Here the different parameter values. So now we have some information. The likelihood is the highest here, around, let's say, 0.8. And then our posterior state of knowledge is just a combination of these two. So in the beginning, we did not know much, that we gained some information from the data. So now this is our updated state of knowledge. Now, in other cases, we have some stronger, more informative prior knowledge, as you can see in the second line. Now, if you gain information from the data through the likelihood function, let's say that this is exactly the same information you gain from the data. Then in this case, now your posterior is going to be a compromise between the stronger prior beliefs and the information you gain from the data. Now, but when you have the same prior state of knowledge, but you have a lot of information from your data, in a way, the data will dominate your posterior inference. So the information from the data will overcome your prior beliefs. And you can see here that the posterior state of knowledge and the third line is actually very close to the likelihood function values. Okay, but having some prior knowledge is often useful, especially when you don't have much data. Here is a small scenario as a fun example of that. So this is just to show that while Bayesian inference is often actually criticized for subjectiveness because of the prior distributions we have to specify, it is very often actually very useful, and it could be a useful part of the inference. So now we know how to calculate the posterior distribution. How do we actually do inference with the posterior? So typically, when you have a posterior distribution, as I showed you for the parameter, you can just calculate its mean, mode, or median to get a point estimate. So you can get a point estimate the same way as you would get in the classical inference framework. And the standard deviation of the posterior distribution would represent your standard error. Now, with very simple models, like the one actually I showed you in the 3 lines before, that was just a beta binomial model, you can actually calculate analytically the posterior distribution. But with more complex models, we use Markov chain Monte Carlo algorithms to get a large number of samples from the posterior distributions. So the most commonly used software packages for that are Stan and JASP. And you can implement practically any Bayesian models into them, but they don't have a graphical user interface. The software package that I'm going to cover today, JASP, has a graphical user interface. It's more user-friendly, but actually the range of models that you can fit in it is a bit more limited. However, there are always novel models added to it. STAN is actually named after Stanislav Ulam, a pioneer of the Monte Carlo methods, and JAGS is just like an acronym for just another Gibbs sampler. And I will tell you what the name JASP means when we get to that. Okay, so then the next big topic that I would like to cover is hypothesis testing. I just want to make sure that we are still on the same page. So if you have any questions, this is also a good time to ask them. Okay, then let me ask you a question. Let's say, would you want to stop a study if people seem to getting worse, or if there is clearly no treatment effect, but your final analysis not to depend on whether you peeked into the data to make that inference? Or would you like to state the level of evidence in your data in favor or against the hypothesis? Has it ever occurred in your research, Pravani?
Not really, because I'm not a Bayesian analyst. So I was going to like, before you expecting the answers to the question that you asked, there are two wide overall questions in the chat that might be,
Yeah. So with a massive amount of data, is it worth doing a Bayesian analysis since the prior has little impact? I would say yes, because the inference you can do when you implement Bayesian analysis is actually much more intuitive. So for me, in a way, the interpretation of a parameter estimate in terms of posterior probabilities is extremely useful and very translational if you think about clinical applications. So to say that you get, for example, a posterior probability distribution of, in my research, for example, of someone showing cognitive decline across 5 years. So there is a parameter that summarizes that, like how large the cognitive decline is. And then you can just set a threshold and you can say that this is the probability, and in the Bayesian framework, you can make such inference saying that this is the probability that the decline is larger than 0.5. Like there's a 90% probability that they decline more than 0.5 across 5 years. Like let's say that their processing speed in terms of millisecond declined more than 200 milliseconds over 5 years. The probability of that is 99%. Then you can go into that probability distribution and put your threshold somewhere else. And you can say that the probability that this person declined 800 milliseconds in the past 5 years in terms of their processing speed is 65%. So you can make this kind of very nuanced, intuitive inferences that are in a way not possible in the frequentist framework.
Can I ask a follow-up question on that? Is it usually, I mean, I don't know whether how relevant that will be. So is it usually fair to make a, like imagine that if you have large amount of data, that the information you have about the parameters would also be relatively large, that you know something from your background about the parameters that you're trying to estimate?
So that's just defined by the prior, like the previous background, but the parameters. So everything that's then afterwards, it's in the posterior, it's coming from the data. So in a way,
so what I meant is that you can adjust the prior based on what you know about the parameters though, right?
Definitely. Yeah. And what you can do is you can do this kind of sequential studies. So you do study one, you learn something about your parameter, and I will have this on a slide that today's posterior is tomorrow's prior. So in the next study, you can already use it to increase accuracy of your parameter estimates if you know something already about the parameter. And sometimes it's just small things. Like sometimes it's just like something weakly informative. For example, when I'm talking about decline across years in terms of milliseconds, I know that it's not going to be 20,000 milliseconds because no one is really declining. So like sometimes it's just about the range of the parameters, but all that just helps the inference and makes the inference more accurate.
So the second question is how to answer.
That's a $1 million question. Yeah, so definitely it's definitely a hard question because I would say that if you don't have any knowledge about your parameters, then there are good recommendations. For example, JASP has recommendations for some default priors that would not bias your inference, or Stan would have recommendations. Stan would also set priors for you if you don't define them. And those are set in a way that they are non-biasing, but they help in a way the algorithms, so that like they might just check the range of the data and they set something that makes sense on that range of the data. And sometimes the range only means that for variance parameters, we don't consider negative values. That's already very useful when trying to do a parameter estimation. And then when you do know something, then you have to, in a way, formalize it as a probability distribution. And there are applets, for example, that could help you draw these probability distributions online, like whatever makes sense, whatever could be formalized in terms of your existing knowledge.
Yeah, and it is, I mean, correct me if I'm wrong. So it is usually my experience when you're choosing a prior that when you start working on Bayesian analysis, you'll figure out like few of favorite priors to begin the game, right? And then you keep updating as what you learn.
Yeah, indeed. Yeah. And that's a one wonderful thing about Bayesian inference.
There's one last question, Zita, about how close or distant non-parametric statistical approaches to Bayesian approach.
Well, non-parametric approaches are nice in the sense that they don't make that many assumptions. Just like in Bayesian statistics, you don't make assumptions about your sampling plan or like some distribution assumptions you just don't need to make. So in that sense, they can be in a way more flexible and closer to that. But yeah, I mean, in Bayesian framework too, you can have, for example, likelihood-free inference. So like you can go more into the non-parametric Bayesian way.
It's so fair like to think about Bayesian approach as an estimation technique, I would say, right? And now we can go back to your question again. You might have to repeat to everyone.
Yeah, so is it desirable for everyone to try to, like, when it looks like that the study is not working out, you peek to the data and you say, okay, like people are getting worse. And then you could just like stop collecting data, but not that when you come to the final analysis, your final analysis would not depend on whether you peeked into the data or not, or to actually state the level of evidence in favor of an effect not being there or in favor of an effect being there. So I would have hoped that everyone would say that, yes, like this is something that we would like to get out because it's, in a way, it's somewhat common sense. So this is actually a quote there from Pierre-Simon Laplace, who said, the theory of probabilities is basically just common sense reduced to calculus. So it's like, in a way, the Bayesian framework could open up a new statistical tool set to have more nuanced inference. And then this is what this hypothesis testing part of today's workshop would like to focus on. So in frequentist inference, you always have sampling plans. So like you have to condition on those sampling plans to actually, I mean, in classical hypothesis testing, to actually draw inference from your data. And in Bayesian inference, the state of knowledge corresponds to probability distribution on the model parameters or on a hypothesis, as I will show. So in the classical framework, we often do hypothesis testing with p-values. And one of the biggest problems with p-values is that it does not say anything about the amount of evidence in your data. So it helps you make a binary decision, but it doesn't tell you anything. It doesn't quantify the amount of evidence, and doesn't say anything about the probability of the null hypothesis or about the alternative hypothesis. And very often this is the intuitive inference that that people would like to make, researchers would like to make. Now, in the Bayesian framework, we can attach probabilities to hypotheses, just as we attached already probabilities to parameters or parameter estimates, as I showed you before. And there is a measure, we call it Bayes factor, that actually quantifies evidence in favor or against a null or an alternative hypothesis. And we do that by specifying prior model odds. And if we also specify prior model odds, then we can also calculate with the help of the prior model odds and the Bayes factor, the posterior model probabilities. What we can also do is we can monitor and update evidence as data come in. So the Bayes factor is the standard Bayesian solution to the hypothesis testing problems. And what it does, it compares the predictive performance of one model versus another model for a given data set. So what it does actually, or how it works, is that as a model comparison tool, is that it reallocates credibility across models. And I keep saying models, but it's because hypothesis testing can actually be understood as different models competing to describe the same data set. And these different models, they represent different theories, competing hypotheses. They might involve a different set of parameters, different distribution of forms, etc. So let's derive the Bayes factor now based on Bayes rule. So for model comparison, the Bayes rule is applied to the model index M. And before, we had theta here, now we have just a model, like by switching theta to the model index M. So the probability of the model, the posterior probability of the model given the data, equals the prior probability of the model, the probability of the data given the model, and the probability of the data, how much evidence in a way you have in your data. The probability of the data is just a sum of the different probabilities of the data given the model times the probability of the model. So you sum this across the number of models that you are considering. The more interesting part here is the probability, like how to calculate the probability of the data given the model. And here what you have to do is you are actually integrating over the all the model parameters data that you have here to get the probability of the data given the model. So the likelihood of the data for a given model or for a given hypothesis that that model represents is the probability of the data within model M, computed in a way that we marginalize across the prior distributions of the parameters in the model. So you can see that the model is not just the likelihood function per se, but also the prior and the parameters. Now, if you want to compare two models, then you can take this formula and you can put them in a ratio. So you can just take this part here, switch in model, replace the model index M with model 0 and model 1, have these two parts and put it into a ratio. And what you can see is that this part remains the same with both models, and it actually cancels out. What you get at the end is what we call relative posterior model probabilities. And as I said, the M could be switched already for an H for hypothesis, even since the models represent different hypotheses. So what we have here is the probability of model 0 given the data divided by the probability of model 1 given the data. And that equals to what we call the Bayes factor, the relative evidence in your data, and the prior model odds. So let's talk a bit about the Bayes factor. Here, since model 0 is up in the numerator, we would write Bayes factor in a way that Bayes factor for model 0 as opposed to 1, like Bayes factor in favor of the null model, when null and the alternative models are considered. So Bayes factor 0, 1, for example, when it equals 1, then the data are as likely to have occurred under the null model as under the alternative model, like, for example, model 1. Now, when Bayes factor 0, 1 is 5, then the data are 5 times more likely to have occurred under model 0. So you also always have to look at which index comes first here in the Bayes factor, the subscript. Now, if the Bayes factor 0, 1 is 0.2, that means that the data are 5 times more likely to have occurred under model 1, because then you would have something like 1 over 5 here, right? 1 over 5. Now you can turn it around, it's just a ratio, you can simply switch it, and you can say that the Bayes factor 1, 0 is 5, for example, so the data are 5 times more likely to have occurred under model 1. So 1, 5, you just take the reciprocal, it's 5, 1. Here are in blue, you can see the prior model odds. And the prior model odds are set by the researcher to express how plausible models are a priori. So this is your prior on the competing models or on the competing hypothesis. And you can really set this to be something meaningful. For example, when would you want to set it to something meaningful? When you have competing hypotheses, when one is just extremely, you consider it extremely unlikely. For example, when someone is saying that when someone is talking about whether extrasensory perception exists, and this then you might want to, like, based on your knowledge, based on your scientific background, you might say that, well, a priori, I think that it's more likely the hypothesis that extrasensory perception does not exist. A priori for me is higher than that it actually exists. Or if you see an octopus called Paul, who is predicting the outcomes of the soccer World Cup, then you can also set prior model probabilities saying that, well, I mean, most likely this octopus is not really that, you know, like is not really a magician who could see the future. So most likely I will give a priori a bit more weight to that model that would say that this octopus doesn't have any abilities to predict. Or as Carl Sagan put it, extraordinary claims require extraordinary evidence. So if you set your prior model odds in a way that you give more weight to one model than the other, then you need more evidence from the data, more evidence from your Bayes factor to overcome that. And it's reflected, that would be reflected in your posterior model odds. Most often, what we would do, though, is we would just set it to be 1, the prior model odds to 1. So that would mean that the two models are equally likely a priori. And if you do that, then you can very easily also derive the posterior probability of the model. So for example, if I write it out for the null model, then you can just, so if the models are the same in terms of their prior odds, so they are equally plausible in the beginning, then the probability of the, for example, the null model given the data is just the Bayes factor in favor of the null model divided by the Bayes factor for the null model plus 1. So all you do is you take these odds, right, and then you transform it into proportions. So a Bayes factor of 3, for example, here, you can see here it's already written out the probability of data given alternative hypothesis divided by the probability of data given the null hypothesis could be 3. So you can transform them into odds. And these odds here actually reflect you can just transform them right away to percentages for posterior model probabilities. I have actually a table here to show that to you. So as I said, that if the data provide ambiguous information, then your base factor will be around 1. So no strong support for either the null or for the alternative model. If it goes up, for example, to 3, then it means that the data weakly supports the null hypothesis. And with equiprobable models, this would mean that the posterior model probability is 75%. Now, if the data strongly supports the null hypothesis, so if you have a base factor 0, 1, that's 10, then you can see here that the posterior model probability in favor of the null hypothesis or favor of the null model is 91%. And then you go the same way in the other direction as well. We often assign labels to the strength of evidence. You can see here that between 1 and 3, we would say that the evidence is anecdotal. So there's like a bit more evidence for one or for the other, but it's not much. And usually we would consider evidence when there is at least 3 times as much evidence in favor of one model or one hypothesis than the other. But even at that time, we would just call it moderate evidence. This is how much we can learn from the data. There's some evidence, but it's moderate. And usually above 10, we consider a base factor showing strong evidence. But you might not want to put these labels. You might just want to report the base factors, so you can just have also a continuous measure of evidence. Okay, so to summarize, I believe that researchers often have a Bayesian intuition to significance testing when interpreting p-values. I've heard my students or some of my colleagues say too that the probability that the alternative hypothesis is true is very high given how low the p-value is, etc. But you can absolutely not make statements in the frequentist framework about the probability of the hypothesis being true. Why? Because in the frequentist framework, it's nonsense, since the theory is true or a hypothesis of a model being true is not a repeatable event. So you cannot make probabilistic statements on a non-repeatable event. So that all comes from that interpretation of probability that I mentioned in the beginning. So theory is true or not true. On that, no probabilistic statements are allowed in the frequentist framework. Moreover, the base factor can quantify evidence not just in favor or against, not just in favor, but against the null hypothesis as well. And of course, of an alternative hypothesis to against the null or in favor of a null or an alternative hypothesis. And that's really useful, for example, when your null hypothesis, as I said before, maybe that sometimes you just want to show that the risk is not there, like you have like an old treatment or an old drug that caused a certain side effect. Now you have a new treatment or a new drug, and you want to show that there is no link, there is no evidence of an effect there. So in this way, it can be really useful to quantify evidence for a null hypothesis too. You can pick out which model has the most evidence based on your data from the ones that you considered. And it's also not just a binary decision, you can have continuously scaled evidence, which also avoids the problem of using conventional cutoffs like the p-value of 0.05. You can also continuously monitor the base factor, and there's absolutely no problem with optional stopping. I will talk a little bit more about the sequential analysis and Bayesian framework after the break. So prior model probabilities or prior odds are not the same as priors on the model parameters. So we had this like blue part for the prior model odds, but then in every model, we also have a prior distribution on the model parameters too. And actually to derive the base factors, the prior model odds are not needed, but the priors on the parameters are needed because you integrate over them, as I showed you before. So often when you are just doing Bayesian parameter estimation and not hypothesis testing, what you would choose in terms of priors is something that I referred to before as uninformative prior distribution. So like a very wide, flat distribution on a big, large range of the parameters. And that works well for parameter estimation. It's a bit more problematic when you are actually doing hypothesis testing. Because for calculating a base factor, if you have wide uninformative priors, those are actually corresponding to very complex models or very loosely defined hypotheses. So far, maybe when you were thinking about model complexity, you were thinking about in terms of parameters. And that's still true in the Bayesian framework too, that more parameters mean more complex models, and they make more predictions too, right? But in the Bayesian framework, there's one extra factor to consider, and that's how the choice of priors can affect model complexity. And that's because you must remember from your probability studies that for your probability theory studies, that for every probability distribution, the area under it, under a probability distribution function, integrates to 1. Now, when you have a prior distribution, a prior probability distribution that's very, very broad, very, very wide, then relatively low probabilities are assigned to the parameter regions, to some like segments of the parameter space. So that means that that these spaces include the parameter space, for example, where your likelihood would be really, really high. And thanks to the information you gained from the data. So the predictions are good there, your likelihood is high, but overall your prior is very, very low. But then there are places where the likelihood is practically 0, and those with a wide prior would still get some prior probability. So they would still have some probabilities. So taking all this together, when you calculate the marginal likelihood, then it would result in a lower likelihood if you have wide priors that are spreading the prior probability too wide than if you have like some kind of more specific priors. So the solution to that is really to have some well-defined hypotheses with what we call weakly informative priors that make sense, that actually formalize your understanding of the hypothesis. And these are worked out for general problems in JASP. And I can see that there are 2 questions in the chat. Will you share the deck after the workshop? Yes, definitely. Any more questions before we go into some demonstrations with JASP? Okay. So then let's start. Bayesian data analysis with JASP. So JASP is already all around the world. So if you haven't heard about it, it has been used to teach statistics in many universities in the United States as well. It's a popular statistical software with a graphical user interface. And its popularity is also due to its competitors as PSS or SAS being expensive, inflexible, and sometimes even outdated. So JASP is free and open source, and it's more intuitive in a way than using R, because that usually requires the knowledge of computer programming. JASP has an attractive graphical user interface where output you will see is requested and adjusted on the fly just by dragging and dropping variables or like ticking boxes. And this really, when you teach statistics, it's nice in the sense that it allows teachers to focus more on the statistical concepts than on computer code. And students sometimes feel safer because they are not afraid of making a programming error. So yes, I said that it's used for teaching statistics everywhere. So not only Bayesian statistics. In fact, any kind of intro stats class can use JASP, even those that only teach frequentist statistics. And then maybe once the students get like it, they are doing frequentist statistics with it, then they will also try out the Bayesian modeling. So Bayes' theory is really appealing. I feel like that I've made a good case or why you would want to be a Bayesian. And you could also see from the dates and when Bayes lived, that it has been known for centuries. So the theory has been out there. Why isn't everyone Bayesian? So one reason is definitely that, that applying probability theory for complex model, like in practice, needs computational power. And it just recently, this problem recently became solved, like it's easily computational power is easily accessible now. But it also needs background in math, stats, and programming. So this is where JASP will help out. And JASP stands for Jeffrey's Amazing Statistics Program, in recognition of Bayesian pioneer Harold Jeffreys. It's developed by the Psychological Methods Unit of the University of Amsterdam. And so it has an intuitive user interface, includes both standard and state-of-the-art procedures. It's being developed continuously. And what's really behind it, though, is R. So it uses R packages and it provides you with the R code it's running behind the point-and-click interface. So R and R packages constitute, in a way, the statistical nucleus of JASP. So in a way, then JASP may be considered just a GUI for a specific set of R packages, if you think about it like that. And it would definitely not exist without the statistical foundations provided by R. It comes with a lot of resources, including YouTube videos, blog posts, manuals, articles, and you see even some artwork that I'm putting here and there on my slides. And it also has several example data sets. And I thought that for your first exposure, maybe your first exposure to JASP could be something entertaining and funny. So we are going to first test the South Park hypothesis with JASP. And this is just a toy example to demonstrate how we can look for evidence in favor of the norm. So I don't know whether you are South Park fans or not, but there is an episode in which Eric Cartman pretends to be a robot from Japan, the Osmo 4000, and then he's kidnapped by Hollywood movie producers, and he's like forced to generate profitable movie titles. And so Cartman manages to generate thousands of silly ideas, and lots of them, like hundreds of them, feature Adam Sandler. And so it's clear in a way, or like most of them, I think, feature Adam Sandler, but it's clear that the writers of South Park believe that Adam Sandler movies are profitable regardless of their qualities. So as long as Adam Sandler is in it, it's going to be a successful movie. So the way we could put this hypothesis is, for Adam Sandler movies, there is no correlation between box office success and movie quality. So movie quality, for example, quantified by freshness ratings on Rotten Tomatoes. So this is like the no difference, no correlation hypothesis that we would like to test. Now, in orthodox statistical framework, we could not address this question because what we are testing here, that there's no link between these two variables. I want to show you, before we go into the analysis, just very quickly, how flexible JASP is in terms of even editing the data within JASP. So if you click on this little triangle, then it will pull up the data, or you can just drag it a bit to the right if you want to see less of it. And if you click on this little icon here, this filter icon, then you can just add, for example, filters or transformations of your data right here with this graphical user interface. So if you thought that, oh, he only had 2 movies in 2000, 2001, they are not really reflective on for this question, you could just filter out the movies, the movies from 2000 and 2001. Now, if you run the analysis, But we can see that even just by plotting the raw data, you see the how many $1 million it generated and the freshness ratings. It does not look like that there's much correlation between how good the movie is or how much money it generates. And JASP displays the base factors. And you can see that the base factor in favor of the alternative hypothesis is below 1, so 0.22. But if you just switch it around, then you can see that the base factor in favor of the null hypothesis, so no correlation, null hypothesis of no correlation, is 4.4. So that means that in the data, there's 4.4 times more evidence that movies starring Adam Sandler are more profitable regardless of their quality. And as I said, this that there is no, like this could be anything else too. Like if you want to show that there is no evidence that the treatment is correlated with an unwanted outcome, this is the same kind of questions that you would want to ask. Now you also see that for this correlation coefficient, it provides a posterior probability distribution. So this is the posterior distribution of rho given the data. And you can see that the peak is around 0. And then with the dashed lines, it's showing the prior distribution. And for this problem, since the correlation is limited to be between -1 and 1, it's just the default JASP prior would be actually just a uniform distribution between -1 and +1. So distributing probabilities equally on the range of correlation coefficients. It gives a point estimate for the correlation coefficient, and it gives a 95% credibility interval, which can directly be interpreted the way students usually misinterpret confidence intervals. So the credibility interval can be interpreted that there's a 95% probability that the true parameter value actually lies in this interval. And here it is graphically displayed. Now, if you wanted to, with this posterior probability functions, you could also do some more informative things. So you could think about trying to quantify the probability that this correlation is at least medium size. Like, let's say that this correlation is at least 0.3. At least a 0.3 positive correlation between movie success, like box office success and movie quality. Then what you would do is you would put a threshold there around 0.3, and then you would integrate over this part of the probability distribution to get the probability that this correlation coefficient is actually larger than 0.3 based on the data. So you could see that if you integrate it over here, probably it would be a relatively low probability, like there's just a 10% probability based on this data that there is a medium-sized positive correlation there. So besides the base factor, thanks to the posterior probability distributions on the effect sizes on the parameters, you can also make inferences, nuanced inferences like that.
Zita, can I ask a quick question? With the previous slide, when you say that the cumulative distribution from that point that can be computed, does that mean that JASP can do it if you give a cutoff, or does it mean that, because it seems to very obvious if the posterior distribution is a very nice form that you can actually do it manually by an integral, but if it is not a nice form, that it seems like a little tricky, right?
Yeah, so then what we do is Monte Carlo integration.
Okay.
So when we have 10,000 samples from the posterior, then you just count the samples that are above 0.3.
Okay, gotcha.
That's a good estimation of the integration of the analytical integration of the posterior.
So you basically,
JASP cannot do that. But I wanted to still illustrate something about the Bayesian framework that I really appreciate.
Yeah, for sure.
Yes, yeah. It's not yet implemented in JASP. It might be. So you can also on the forum, you can just add things like add features, like they have a dream list feature selection thing there going on.
And another follow-up question that I have is about the sample size of the actual data that you might be using for an analysis. Is that something that one needs to be aware of, that, for example, in this small analysis that you're doing, it looks like you have about, I don't know, about 30, 40 data points there, right? So is that something that, is there like some sort of a rule of thumb or something that someone should be aware of if they're using techniques or not?
Bayesian inference remains coherent with any sample size.
Cool, okay.
If you have a small sample size, you have much less information in that. And the Bayesian framework will, the Bayesian analysis will just take it into account naturally. If we had less data points here, then this posterior distribution would be much wider.
Yep.
Like a much larger amount of uncertainty. So the standard deviation of this posterior distribution is what would provide you with the standard error.
Got it. Thank you.
Okay, so before, oh, wait, I have one more question in the chat. Yeah, thank you. You killed Kenny. Yeah. Let's see. I wanted to do a very short demo of JASP before we have a break, and then we can have like a 5-minute break. And if you haven't installed JASP, oh, sorry, I put JASP, but this is just a typo. So JASP. If you haven't installed JASP, then please do that, because there will be some do-it-yourself exercises after that. So I will need to reshare my screen once I pull up JASP. So how did I get to this screen? I click on the hamburger, the blue hamburger here, and I go open data library. And here you have all the example data sets JASP provides for you for practice or for teaching purposes, grouped with the different analysis techniques that they are best known for, like that they are best for to demonstrate. So I went on regression, and then here is Adam Sandler. Now, if you click on it like this, like I'm showing it now, that you click on this like large text here, then it will pull up the data set and some already implemented analysis results. If you only click on this part up here, then it will only pull up the data set. So then you can just, for the students, you can just do the analysis on the fly like that. But let's just pull up now the actual analysis that is featured. So the null hypothesis test that I showed you was a two-sided one. So I was saying that that I didn't know whether they would be positive or negatively correlated. I was just looking for whether there was like a difference in correlation. But what they did was, in their example code here, is that they said their alternative hypothesis has correlated positively. So this is what I had, or just correlated, so two-sided alternative. And you can see this is how it changes on the fly, just when you click. You're just running the analysis. And you can see whether there is just one-sided, then the prior is only set between 0 and 1. So here you have, like, in a way, a less complex model, a better specified alternative hypothesis. So here actually the base factor is showing that it's 5 times in favor of the null hypothesis. I had a question, I was just looking at the chat. Could you recommend good resources from intro level to advanced level on Bayesian statistics? I know there's a bunch of them, but from your teaching. Yeah, so I have a couple of recommendations at the end of the presentation. They're like more specific maybe to JASP. But then at that time, I'm happy to talk about some other Bayesian books. There's one that I just love. It doesn't actually feature JASP, but it's based on STAN. So I will talk about it at that time. I can put the name of it here, just in case I forgot. Why would you need a log of the base factor? It's just another way of scaling it. It's completely like the inference based on the log scale or not on the log scale would remain the same. It's just some people prefer showing it on the log scale. So here, then it will just show it on the log scale. It's a bit easier to see in terms of like a negative would mean like support for the other one. And the positive would mean support for the one that you put first in the base factor index. So maybe it's a little bit more intuitive. It's scaled in a way that it's comparable, like it's not easy to see that a base factor of 0.2 and 5 is actually the same in terms of how large it is. Just one is in favor of one, or the other is in favor of the other. So 0.2 and 5 are the same, like base factor effect sizes. And with the log scale, this is like clearer. So a log scale, just like it's useful for other variables to log scale it could be useful and more intuitive in this case too. So here is the log. Here is like if you change it here, then right away it shows you the evidence for the null, which if you express it as evidence for the alternative is around 0.2. It's just a bit harder to see with 0.2 and 5 than on the log scale. Here is the plot that's just displaying the raw data. Here's again our priors and posteriors.
Zita,
here, yeah.
Are you sharing the correct screen that because I think it's not like whatever you're updating on your end, it's not reflective.
Oh, I'm so sorry. So I for me on both screens now it shows that I'm scrolling. Does it show it for you?
No.
And it's really showing it on both. So let me try to share it again, at least so that you're on the screen where I am now. Can you see me scroll now?
Now, yes.
Ah, that's interesting. Yeah, okay, great. So I was just showing that here's the base factor in favor of the null hypothesis. And here's in favor of the alternative hypothesis, but log scaled. Minus 1.6. And when it's not log scaled, then it's just the reciprocal of 5.2. What we haven't seen so far is this robustness check. So the robustness check relates to setting different prior distributions on their effect size. And it's practically showing that even It's here. This is where you set it. You see my mouse, right?
Yes.
Actually displaying how extreme the prior should be if you wanted the base factor to be 1. With other examples, I will be also able to show you how different width of the prior distributions, for example, for t-tests, would influence the base factor. But here you can see that it doesn't really matter what kind of prior you would use. There would be moderate evidence for the norm. And one thing that we will continue with after the break is this sequential analysis or sequential updating of evidence of information. You can see here the sample size on the x-axis, and you can see that as the sample size grew, we had more and more evidence in favor of the null hypothesis. And it crossed the line of the 3 around 16, and then it's still fluctuating a bit, and it stays within the region of moderate evidence. So this is how, in a way, every time a new data comes in, you can just look at how much evidence you have in your data in favor or against the hypothesis. But I will talk more about it after the break. Let me see, there are some questions. Oh, we are not seeing the changes. Yeah, okay, great. So are there any questions before the break? If not, then if you haven't installed JASP, then please do so. And we'll meet again, let's say at 2:50. Does that sound good?
That's good. Thank you.
Thank you. Welcome back, everyone. Okay, let me share my screen again for the second set of slides. Okay, I think we are good, right?
You're showing the slides, right? Not the
Yeah.
software. Okay.
And you saw it change, right? It changed. Yeah. Okay. So let's talk about sequential analysis in the Bayesian framework. So assume you have just finished conducting a study and you didn't do anything fancy like planned interim analysis with group sequential trials or anything, but you just finished your study and you are comparing your target outcome in your treatment and control groups with a 2 independent means t-test. And you get a p-value of 0.06. Wow. So do you think that you need more information? You draw a conclusion? Would you like to maybe collect more data? What would you do?
The regular recommendation would be to collect more data, right?
And can you actually do that, or what can you do? Like, is it reasonable? Is it what people do?
This is where researchers hate statisticians.
So, and I sort of like, I do think that collecting more data sounds like a perfectly reasonable strategy. Like that's what everyone would just think about. Like, yeah, I just don't know. Like, it looks like there is something, but so it's like, it sounds like a perfectly reasonable strategy. So because you collected some data, the results were not conclusive. So why not collect data until the results are conclusive? What's wrong with that? But honestly, I don't think that there's anything wrong with that. I think it's like sort of a reasonable, sensible, or rational thing to do. And often in real life, that's what every researcher would do. However, unfortunately, the classical theory of null hypothesis testing forbids you from doing that. When you got the p-value, it was assumed that all the data were in and it was collected based on a very specific sampling plan. And then there's the other interesting thing that now that even if you decide that, okay, this was it, I'm not collecting, I cannot collect more data, the experiment is over, there are only two possible outcomes to consider, right? That's just a binary decision that you can make in the frequentist framework. So you cannot quantify evidence, for example, in favor of the null hypothesis, even though you cannot reject it either. Okay, so in classical hypothesis testing in the frequentist framework does not allow for such decisions without inflating your type 1 error rate. And while the Bayesian framework is actually not explicitly designed for type 1 and type 2 error control like the frequentist framework, it's really just a framework for information updating, for learning from data. It does provide a valid inference at any stage of the data analysis based on how much information you have in favor or against your hypothesis. And of course, like I can never say it again, or also based on your prior distributions, how you set it, because in the Bayesian framework, prior distributions are really integral parts of the model. So let's have an example to demonstrate that. And this is based on the data set called weight gain. That's also in JASP. And it provides weights of 16 participants before and after an 8-week period of excessive calorie intake. So they made these participants just really eat a lot. And I'm going to demonstrate a one-sample t-test with that in JASP. First, we just test the simple null hypothesis of no weight gain. Like that, excessive diet didn't work. People would just still not gain weight. Their body would just get rid of the extra food. Second, the second hypothesis we are going to look at is, let's say we put in place some controls and we have very specific expectations on with the amount of extra calories our participant consume, that they should be gaining 10 extra pounds. Like we are really careful with how much food we give them so that it will work out on average as 10 pounds of weight gain. So what we want to do here is to test an informed null hypothesis where we want to actually state evidence in favor of the null hypothesis. So we'll do the first analysis first and then the second. And I'm actually not going to do that directly in JASP, but I pulled out screenshots on slides so that I can.
A question for you that might be relevant to one of your previous slides. So I'm going to interrupt. I'm sorry.
Yeah, no, that's fine. Like I'm happy to.
So it's referring to, I think, the question that you asked whether to collect the data or the information question. Probably more relevant is what size of clinical effect was chosen when determining the sample size?
Was it for this weight gain data set or
I think this data set, when you asked the question whether when the p-value is 0.0612 or something, right? So there were two options that you gave. One was to collect more data, and the other one was the information related question. I think the question is related to that. Maybe it's better if you unmute and explain. I'm not sure.
Yeah. Yeah, I mean, it's probably a moot point at this point. Sorry, but I was basically saying in response to whether we should collect more data or not, I would argue whether if you set very strict standards when you consider a clinical benefit, then maybe it's possible that you were just too strict with how much of a benefit there is. But if you're very liberal and being like, hey, only if there's a 1% difference, and you get 0.06 still, then I might argue, well, 1% is still too small regardless. And so if you can't show, if you can't show a difference that, is of a large magnitude, then for sure a smaller magnitude you're not going to be able to show, I guess is what I was getting at. So what's the point of if the a priori sample size was determined based on a standard that was already, skeptical. That's it. Sorry, probably a little bit late.
Indeed. So it might be a waste of resources, even in this case, to say that we would want to collect more data. So it's a bit more nuanced than how I presented it, because if like we have some effect size and the confidence interval or the credible interval in the Bayesian framework is already very narrow. So it looks like that there's a lot of information in this data. Then even though we collect more data, it might be that it's not going to change and it will never reach significance, or we will never detect an effect, because this is what it is indeed. And so that's a great point. And also considering maybe a stopping criterion that does not involve calculating p-values, but just looking at confidence intervals or credible intervals could work really well in this case as well. Okay, so let's get back to the weight gain, and here is how we find the weight gain. It's in the t-test folder, the same way as the category is now t-test weight gain. Click on it. And you can see that you can set a test value actually for the one sample t-test. And this test value for our first question was set to 0. And we were just testing simply the alternative hypothesis that it's not equal to that test value. And you can see that there is huge support for the alternative hypothesis, like a huge Bayes factor, which is not surprising, given I will just show you a plot of the data in a second. So it looks like that indeed there's a lot of evidence that the excessive calorie intake diet worked, and participants gained more than 0 pounds with the diet. So here we are showing the Bayes factor in favor of the alternative hypothesis. And here is the alternative hypothesis specified. Now, if you wanted to, just like before, you could check it for, you could change it to show it in favor of the null hypothesis, or to show it on the log scale. And here is our descriptive plot that you can also get in JASP. It's a really nice, they call it rain cloud plots. And this is just showing the difference score that was calculated based on the before and after weights of the participants. It looks like indeed that they were gaining a lot of weight.
So
here is our, right, yeah, go ahead.
I'm sorry, I think you mentioned this, you're just showing the slides, right? You're not changing, like it's not actual JASP that you're showing, because
no.
I just wanted to say that if you go open the weight gain from the t-test, it seems to me that it actually just brings up the frequentist approach.
Yeah,
automatically. Okay. Because if someone is following, I think they would see something else than what you're showing.
Yeah,
right?
yeah, that's true. Yeah, I will have an exercise, I believe, with that soon. Okay. Yeah. So that's why it's a good data set for that, because actually the Bayesian analysis is not shown for this data set. So here is our effect size prior and posterior. You can see my mouse, right?
Mm-hmm. Yes.
And here's the Bayes factor. Here is the estimated effect size. It's around 2. And actually, for all the t-tests, JASP deals with standardized effect sizes. So it's in terms of standard deviations from the test value in this case. And dealing with standardized effect sizes is really nice in terms of defining default prior distributions on that. Mm-hmm. Because when we have standardized effect sizes, we actually have a very good idea about what makes sense in terms of standardized effect size and what would not. Like, it doesn't make sense to think of a standardized effect size of 50 or 100 in social sciences. That would never happen. So when you set prior distributions, then it's their default is called the Cauchy distribution with scale 0.707. And in this case, for this analysis, I chose to have an informed prior distribution. So I did not take their default, and I said that I just take a standard normal distribution on the effect sizes, because it reaches between -4, most of its weight is between -4 and 4. So that's like a reasonable range for me for the prior distributions. So we have an intrinsic scale in a way with the standardized effect sizes to set a prior distribution on. This is, I believe this is sorry. So this is actually this was the Cauchy distribution, and this is this might be the normal distribution for the prior, but now with standard deviation 2. So if you want, you can stretch it out a bit more. You can see that in this data, there is so much evidence for the effect that the base factor still remains very, very high. And here is now, okay, so here is their distribution, the Cauchy distribution with the scale 0.707. So this is their default for a problem with standardized effect sizes.
Zita, can I ask a quick question?
Yes.
Oh, so I just want to make sure I haven't gotten lost. So what we have overwhelming evidence for here is that people gain 10 pounds?
No, we are still just going with the test value of 0.
Okay.
We are still in the first analysis. I'm sorry. Yeah.
Okay.
Just for the first analysis, I was showing the different priors, like the different options for the priors. So we had a prior with a normal 0, 1. We had a prior with a normal 0, 2. And it didn't really change a lot, or their default prior, the Cauchy with 0.707. So just like some prior sensitivity analysis, but the data is overwhelmingly saying, of course, in this case, that it's different from 0.
Okay, thank you.
For the question. So I wanted to just spend a little bit of time on the Cauchy distribution, because that's not something that most of us would be familiar with, and it's like an integral part of JASP. So when comparing to a test value, like in one sample test, or comparing means in a 2 sample test of 2 different groups, it's more generalizable to set prior on standardized effect sizes. And remember that wider priors would mean, in this sense, more complex models, because a too diffuse prior would distribute the evidence too widely. It would put weight on some unreasonable effect sizes like 50 or 100. So we would know, for example, that the standardized effect size of 1 is already rather large in social sciences, and above 6 is unlikely. So we can formalize it in a way that we need a distribution for the effect size. It could be a normal distribution with 0 and some variance for that effect size delta. And there we know what a reasonable range is for this variance. And if you set it, for example, to 1, that's what we would call in general a unit information prior. It would give exactly 1 unit of information to the inference. But if you integrate over this variance parameter here, you actually get a Cauchy distribution. Here are some example Cauchy distributions. It's a nicely scalable distribution. You can just put a scale parameter R here, and that's what's displayed in JASP, like how large you set the Cauchy distribution. And if you, for example, expect very, very small effects, then maybe it's better to have something even smaller than the 0.707, so that it's a bit tighter if small effect sizes are expected. And the JASP default of a Cauchy with a scale 0.707 means that the absolute effect size under that prior has 50% of chance of being greater than 0.707. So 50% is within, 50% is outside. Larger ways of R support larger effect sizes. Or if you have ever heard of Jeffrey's prior, for example, that would have a scale parameter of 1 here. So this is just a small interlude on Cauchy distributions. So let's get back to our analysis, and let's see how we sequentially updated the evidence as the sample size grew. And you can see that already after 3 participants the evidence was close to 10. After 4 participants, it's already crossed the strong level of evidence for this null hypothesis. And here you can also see that it doesn't matter whether our user-defined prior, so the prior we chose, or we choose a wide or an ultra-wide prior, the evidence is more or less the same for these different priors. So it does a bit of a robustness check or some prior sensitivity analysis for us, the sequential analysis. Now let's do the second one, the second analysis I was talking about. So let's say that we have this very specific expectation of 10 pounds that they would gain on average. The test, then the alternative hypothesis is that they would not gain 10 pounds. And now we are displaying the Bayes factor in favor of the null hypothesis. And you can see that it's 3.6. So we have 3.6 times more evidence for our null hypothesis of 10 pounds of weight gain through with this diet than for the alternative hypothesis of not having 10 pounds, so anything else. So we have like a moderate evidence for the null hypothesis here. And you can see again, our effect size now is centered on 0, but here we are still comparing to the test value of 10, but it's standardized effect size. You can see the prior, posterior. I'm just using their default Cauchy prior here. And I haven't really said anything about the spinner here, but on this pizza plot. But so like you could like think about it like there's like if you had a spinner on this pizza plot, then you spin it, and if it ends up in this small area, then this is how surprised you are, like that it would like end up in this smaller area. So it's like it's just some graphical illustration of the surprisingness of the data under the null or the data under the alternative hypothesis. Here is some robustness check. Like even with 3 different prior settings, there's moderate evidence for the null hypothesis being true. And you would need a very extreme prior, like scale parameter on the Cauchy distribution to actually get a Bayes factor that would say that there is no evidence one way or another. So that's like in terms of robustness, it looks like that our results are robust to the different prior settings. And for the second analysis too, we can have some sequential analysis. And you can see here again with the robustness check, with the different prior settings, you can see that it looks like that there's moderate evidence for the null hypothesis being true as the data gets larger. Now, if you go up in the Bayesian one sample test part of the analysis and click on this R button here, then you can actually see the R script behind the calculation. So it displays the R script. So if you just wanted to publish the R script instead of talking about it in a way that you analyze data in JASP, you could just say that, hey, I analyzed it in R. This was the code. You could share the code more easily in a paper. However, I also have to say that whatever analysis you do, and I can demonstrate that too later, but whatever analysis you do, you can save it as a JASP file, and you can right away upload it to the Open Science Framework, for example. And then that JASP file is going to contain the data you analyzed together with your analysis setting and the results. And even better, in the results section, you can add annotation. You can actually spell out the results and interpret the results and save that together with your JASP file. So it's very user-friendly in that sense. So I think it's time maybe for you to get some self-exposure to JASP. So I have a small exercise for you. Let's assume that you expect that people gain more than 5 pounds when they get the excessive calorie diet. So this is a one-sided hypothesis that would be nice to be tested in JASP. So open JASP and find a weight gain data set and click only on the data set. So you don't pull up all the other analyses that are already part of it. Just click only on this part, as I showed you with the Adam Sandler example, and run the analysis as a Bayesian one sample t-test, and then we could come back and discuss in, let's say, in 5 minutes what you concluded. And if you have any questions in the meantime, I'm here, so feel free to ask. Okay, so I saw some results in the chat already. I got 1102 for the base factor in favor of the alternative hypothesis. So I think that everyone should have been getting something around that number. What was your experience? Was it easy to use and interpret after this like short introduction to JASP?
On my end, yeah, I would say it was easy enough to use. I'm still trying to see if I'd use it more often than the standard frequentist statistics, but I suppose that's part of the point of this.
Yeah. Yeah, definitely. It's just, you know, if you want to calculate some correlations for like first stage exploratory analysis, for example, but then, I mean, for like these parts of JASP that we have covered are only for that, like very, very simple hypothesis tests. But I want to say a couple of words soon about the more complex parts as well. Very intuitive, especially with their data libraries. Yeah, because you can like learn on your own too, and just try things out. Very user-friendly. So everyone then was able to carry out the analysis. You got more or less this, I believe, that I display now on the slides. So overwhelming evidence that the participants gained more than 5 pounds. So overwhelming evidence for the alternative hypothesis of being larger than the test value of 5 that we set for the different scores on before and after weights. And you can see in the sequential plot too that the evidence was accumulating really fast, regardless of the prior settings in this analysis. Any questions about this? I think it was a good warm-up exercise, like for like a first exposure with JASP. So let me just close with some final thoughts on sequential analysis. And then afterwards, we will do something that's a little bit more challenging analysis in JASP. So I was showing you these nice sequential plots, but it's not every module in JASP that you would get these like nice graphical ways of plotting information accumulation. But that doesn't mean just because they are not implemented for every module that that you cannot do them like manually or like so the Bayesian principle of being able to do sequential information accumulation, sequential inference applies for every context, even if it's not implemented in JASP. Like for example, here I'm showing an example of the proportions of how many students attending a class on Bayesian inference would use Windows instead of Mac. And then you can see when there's no data, then these proportions between 0 and 1 is it's like flat. And then after asking 7 students, there is more data, 13 students, more data. And as you accumulate more and more data and analyze the data sequentially, you have more and more certainty in your parameter estimate. So the posterior uncertainty, the posterior error decreases with the sample size. And at the end, it looks like that 70% of them, approximately 70% of them are Windows users. So the Bayesian framework can coherently update one's knowledge as new information comes in straightforwardly without the existence of any sampling plan or stopping rule. And another thing is though that, in fact, the order doesn't really matter. So if you start adding 10 more students, or analyze the data at the end, you would get the same result. So you could analyze it in batches, set the posterior as a prior, or you can analyze 10 and 20 and 30, you can change the order, etc. Then at the end, you would still get the same result when you analyze everyone together. And here are some related readings on Bayesian sequential analysis that if you want to learn more about, you could check out. And then let's do one more do-it-yourself kind of analysis. And this will be in the context of eye movement. So eye movement experiments typically employ either free recall or recognition memory paradigms. And there is like set of studies that would ask participants to perform 30 seconds of horizontal eye movement, so looking left and right, immediately prior to the test phase. And according to the alternating hemispheric activation hypothesis, this kind of alternating horizontal eye movements result in alternating activation of the two brain hemispheres. So what they put forward is that this activation pattern may also lead to increased hemispheric communication, which in turn would benefit retrieval of memories. So basically it's saying that just moving your eyes for 30 seconds will help you, for example, recall more words in a free recall paradigm. So they would just boost your memory performance. And so there was, but not everyone agreed with this proposition. And actually, if you read this paper, you can see that there was a very interesting pre-registered adversarial collaboration set up where the opponents agreed in the experimental design and everything, how to test this question. And the data set that came out of this adversarial collaboration is actually now up in the JASP library. So you can find it in the t-test folder. They have, it's not the full data set, so they have two conditions here. Some people just fixated, did not move their eyes for 30 seconds before the free recall paradigm, and others did the horizontal eye movement. So like there are two, like that's our manipulation, the between subject manipulation, fixation versus horizontal. And the dependent variable of interest was how many words they recalled correctly. So the hypothesis was that participants who did eye movements recalled more words. So the first step that you could do is just pull the data set, not just the data set, but the whole analysis, and just check and see and interpret the results that are displayed there. And then afterwards, you could modify the analysis 4 ways. Display the results to show the Bayes factor in favor of the null hypothesis, carry out the sequential analysis, and perform sensitivity analysis by changing the priors, like see how sensitivity is for that. And then change the research question. So the original research hypothesis was participants who did eye movements recalled more words. Now change the analysis to answer the question, does the manipulation make a difference in the number of correctly recalled words? To carry out the alternative analysis too. I think we can take, again, 5 minutes on that, and then we can come back and discuss the results. There was a question earlier that I missed from Carol about logistic regression. So right now it's only implemented in the classical framework. So you can do it in JASP, but not Bayesian, unfortunately. But I know that they are planning to implement that. So that's pretty basic. So sooner or later it will be there, but until the website for the book Bayesian, doing Bayesian data analysis from Cauchy actually has code in R, and I do believe in Stan too by now. In his original book, it was only in R, but I think by now it's in, not R, sorry, it was only in JAX, but now they developed it in Stan too. By the way, if you have to choose, if you haven't used JAX or Stan yet, and you have to choose which one to start with, I would recommend JAX. It's a bit easier to get into first because Stan has this overhead. Like with JAX, you only have to specify the probabilistic model. With Stan, you have to specify an overhead that tells Stan how large your data set is, what type of parameters you have, how large the parameter vectors are, or the parameter matrices. It's a little bit more complicated. So I would recommend JAX, and definitely the Cauchy book doing Bayesian analysis has code for logistic regression. It's not necessarily my favorite book that I would recommend to get into Bayesian analysis, but from the practical point of view, the logistic regression code is great. Okay, so let's see. Any feedback, any comments? How did it go? So you saw now the annotated output they give, right? And we can look at it together too. Let me just try to pull it in. Can you see my JASP screen now?
No,
No?
you still see the slide. That you
Okay.
have.
Let me stop it then. Maybe now. Now it should work, right? So you can see that there is a really nice description always of the problem they are going to demonstrate. Then you can see that they carried out the test and they had a very specific prediction based on theory. They said that the group that is doing the eye move is going to perform better.
So
They
Zita,
had this.
right now, what I can see is just a black screen
Oh, okay.
with a like a yeah, you might have to reshare the screens. And there's also a comment about the Bayesian logistic regression, which might be true because I installed the version today as well, and I can see the Bayesian logistic option.
You cannot.
I can. So if you go down,
okay,
like if you're in the regression option right now, when you're in the Bayesian, you only have correlation and linear regression. In the it seems they have the logistic as well.
Oh, that's great. Yeah, I know that they wanted to do it. You see, like in my version, do you see my drop down? In my version, it's not yet there.
Yeah.
Great. So we do have that. Yeah, so they had a very specific prediction, right? Like the participants with the small eye movement exercise will do better. So they expressed that with this alternative hypothesis. And you could see that there was actually evidence for the null hypothesis. So one thing that we could do is to change it to get a better intuition of how much more evidence we have for the null hypothesis. So they had 11 times more evidence for the null hypothesis being true. Actually, there were lots of things going on with this collaboration. And one thing was that they registered an OSF that as soon as the evidence level goes above 10, one way or another, they will stop collecting data. They will collect at least 20 participants, and then they keep collecting them until the evidence level reaches at least 10 times in favor of one or the other. So this is how they were using the sequential updating in the Bayesian framework to be better with resources, not to have too many participants either. If they can conclude with, I think they had at the end 40 or something participants. Yes, there might be some questions in. Is JASP accepted by HRs? Oh, I would think so, health authorities. I would expect that it is accepted, but it's not that I have. I mean, as much as R is accepted, because it's practically just our packages doing the analysis. So even if JASP is not accepted, and it loads to OSF and everything, so it's well documented and open science friendly. So I would think that it is, but I don't really know. So it doesn't look like that the saccadic eye movements are helping memory recall. And actually, if you look at the, and then I said sequential analysis too. So you can see that how the information was being accumulated. Might take a minute to load. So you can see again, like with any prior setting, there was strong evidence for the null hypothesis. Now, if you look at the data and you want to do some exploratory analysis, but you see actually that people who did not do anything before the free recall task actually recalled more words. Mm-hmm. So if you just wanted to do a simple, that was the last hypothesis, right? Does the manipulation make a difference in the number of correctly recalled words? So if you just want to compare the two groups, you can just change the alternative hypothesis. And this will actually show you, change it back in favor of the alternative hypothesis, that there is 6 times more evidence saying that the two groups are not doing the same. Like there's a credible difference between the performance in terms of recalling words between the two groups. And you can see here is the effect. The effect is to the right, so it's a positive effect size, a relatively large effect. There's a question in the chat. Why I cannot choose the prior by looking at my collected data? Well, because it should be really like whatever prior knowledge you have should be based on knowledge or beliefs that you have before seeing the data. So this is just something that how the framework is built. What do you know before seeing the data? And that doesn't mean that you cannot set priors in a way that you know the range of your data. So you know that you are going to have like a slider on items and the slider goes from 0 till 100. You don't know the exact data you are collecting, but you know the range of the data between 0 and 100. So you can use that information, but you can't use the exact information because that would be some kind of double dipping. So you're putting information from the data in the likelihood and in the prior distribution as well. Okay, any questions about the do-it-yourself exercise? If not, then I will stop sharing. And I have one more JASP demonstration lined up, which is one of my favorites. You can share the wrong screen. And this is about world happiness. So there was a world happiness report that came out in 2017. And what it wanted to see is it wanted to assess which of the 6 life factors predict happiness scores the best. So every country got a happiness rating. Just if you want to look at the data, here is a heat map of the happiness ratings across the globe. And the interesting thing is that if you think about possible models, possible regression models to do this prediction, since there are 6 possible predictors, in fact, there are 64 possible models. Now, what Bayesian inference can do for you is that it doesn't really make you choose a model over another, but it can take into account predictions from several models to give you the best estimate for the effect of these predictors, like the best effect of how well a predictor could predict the happiness score here. So the way to visualize it, I have some artwork for that lined up here. So when you have 64 models, a priori, you don't know which one is going to do better, let's say. So we have all these demons that want to be the best models and are shouting at us, yelling at us, depending on how big they are, to choose them to do the prediction, choose them to be the best model. Maybe one is saying that there's only one predictor is the best model, the other is saying include all predictors. So a priori, you can see they are all the same size. Now you get some data, they will gorge on some data. And then, so we have our likelihood function, we have our data, the world happiness report coming in 2017. And then some posterior model demons will become more powerful and will have a bigger weight. They can shout more loudly because they get more from the data, they gorge more on the data. And they, in our final estimates, coefficients for the predictors, in that, the models that are more likely will be more influential. But all in all, our regression coefficients in the linear regression model will be calculated based on averaging over what all the models are saying. And the less likely models will count less, and the more likely models will count more. So they can all shout in some extent, but the ones that are more supported by the data will shout louder. So let me pull up the World Happiness Report demo. Okay. So this is the Bayesian linear regression option from the regression. Linear regression, so this one here. So we assess which of the 6 life factors predict happiness score. And they nicely work out, like they nicely explain all the variables and all. And then what you get at the end, here's our dependent variable, the happiness score. Here are predictors. And what you get at the end is a list of all the 64 models. I'm only displaying the 10 best here, but I could display all the models, all the 64 models. Their prior model probabilities, which is equally distributed in this sense. Their posterior model probabilities that sum up to 1. So the probability of the model given the data. The base factor for the model. And the base factor in combination of the best fitting model and compared to the other models. So this is maybe the most interesting, and an R-square, like explained variance. So interestingly, the this Bayesian analysis actually picks a model with only 4 predictors as the best model, even though this is not the one that would explain more variance. But the second one is actually the one with 1, 2, 3, 4, 5 predictors. It's still there. So this is how others compare to the null model. So for example, this model if you compare this model and that model, the null model is 1.6 times better. More evidence. There's 1.6 times more evidence for the best model, or 3.6 times evidence for this best model compared to the third model, and so on. But what it does overall, besides giving you this information, so the evidence for the best fitting model, the evidence for the second best fitting model, R squares, etc., it also gives you posterior summaries of the regression coefficients for the intercept and for the 6 predictors. And the mean for these regression coefficients are averaged over all possible models. So they are not coming only from the best fitting model, what the base factor would pick, but their prediction is weighted in proportion of what's the probability that this model would predict the data the best based on these weights. And here are the regression coefficient estimates with 95% credible intervals. And there is some explanation. And if you wanted to, it can show you all models too, but their probabilities for the others are practically 0. So this can be updated. You can see that after 3, 6, 8 models, the rest of the models are not very likely. But it runs all these 64 models for your data and calculates these summary statistics. Or you can just show the 10 best or the 5 best model. And then it gives some explanation too. I think this is a great tool to improve prediction in linear models, because you don't have to pick and choose one model to get the coefficients from, but you can average over what you know by fitting different models. Here are the probability of inclusion of these predictors, a priori, exclusion, and then after seeing the data, this is the probability of inclusion for the predictors. You can see that for generosity, the probability of inclusion after seeing the data is relatively low. So these are scaled between 0 and 1. Mean estimates, standard deviations, 95% credible intervals. Okay, so this was the last thing I wanted to show you as an example, and I'm running a bit low on time, so maybe I can finish, and then at the end we can just spend the remaining of time with any questions that might come up. So I just wanted to say that there's just so much more in JASP and so much more is coming. For example, there are Bayesian.
I'm going to just say that the screens that you're sharing might not be the one that you want to share.
Okay, yeah, thank you. So there's so much more. It's just one big one. Okay, there's so much more. For example, there are contingency tables, Bayesian contingency tables, which are actually based on the joint multinomial distribution, which is a true distribution for these contingency tables instead of chi-square estimation. There are exercises or demonstrations of probability theory in the Learn Bayes module. Yeah, I just wanted to say, I forgot to mention this, but here there's a plus sign. If you push this, you can add modules. So I added here the Learn Bayes module, for example, the machine learning module, there's structural equation modeling module. So there's much more in JASP, in fact, than regression and hypothesis testing. And the newest thing is that they could even provide an interface for JAGs a Bayesian estimation engine that's very general. So you can enter JASP code parameters to monitor, and if you can manage to put your data in the format they need it here, then it will actually run JASP and prepare some plots for you. So it's nice that this is the first time that JASP would have an interface, a user interface, because it's just code-based so far. Okay, so to summarize, remember what we calculated in these examples is only the base factor, so only the evidence based on the data. So this orange part, if you want to get the probability of a hypothesis, of your null hypothesis or so, then you still have to specify the prior model odds, or specify them to be 1, for example, and then calculate the posterior model odds. Base factor is not exactly the same as the probability of the hypothesis. So don't forget about this equation. And don't forget that priors are integral parts of Bayesian inference, and they play a role in your inference and in your conclusions. So always think about your choice and always report it in papers and explain why you chose that. One more topic I just quickly wanted to touch on is whether hypothesis testing is useful at all. So far we were focusing on hypothesis testing versus parameter estimation. So in many applications I don't do hypothesis testing, I just use JAGS or STAN to do parameter estimation. And that really depends on the research question. So there can be research topics, like some of them shown in the class, that only require a simple yes or no answer in a way, like that's a sufficient answer. So you would rather go with hypothesis testing. And it's a promising first step in a way to decide whether or not to tackle a problem further. And when you do estimation, you wish to learn about the size of the effect maybe better, and rather than whether the effect exists. So in any case, just consider these two approaches, and here is just a list of for which procedures estimation is implemented in JASP, and for which procedures is only testing that's implemented in JASP, and there are all the corresponding packages listed too, in case you just wanted the R code. And I wanted to say thank to E.J. Wagemakers, because some of the slide contents are actually coming from his workshops on JASP. And thanks for the entire JASP team as well. You can see that there are many, many people working on this. So logistic regression, which was like 5 days ago, still not there. Now it's already there. I'm really happy to hear that. And special thanks to Victor Beekman for the artwork. And as further reading, I can definitely recommend my 4-year-old's favorite, Bayesian Thinking for Toddlers. It's his best way of not going to daycare in the morning by saying that, but I want to read Bayesian Thinking. It's just like, it's extremely cute coming from a 4-year-old. And this is available online as a PDF. Both books are available online. This is a bit more advanced Bayesian inference from the ground up. So it's a lot of probability theory, and not as practically oriented, for example, than this other green book, Bayesian Inference in JASP, a guide for students. This book also has a recommendation of 4 papers, which are nice and foundational, and that I can highly recommend to read maybe before going into the more practical applications in JASP. On base factor, there's also a thesis from Alexander, dissertation from Alexander Lee, base factor for research workers, in analogy with Ronald Fisher's similar book, which says statistical methods for research workers, Fisher's original book for frequentist statistics. And yeah, and thank you so much for being here today. And I'm happy to still touch some questions. Maybe there's one in the chat.
There's no questions in the chat. I mean, I have plenty, but I want other people to ask. Okay, there's a question. It says, are there common challenges you have encountered in the review process when trying to get studies published using Bayesian analysis instead of frequentist analysis?
So when I started my PhD almost 20 years ago, that was still a problem. So every time I knew if I wanted to publish something, I needed to make a case for why I'm doing Bayesian analysis. I feel like that in the past 5 years, that concern just dissipated completely.
Mhm.
So it's more mainstream, accepted, especially if you can, if you document everything well. So it doesn't look like a black box kind of approach. If you see that you are open about sharing your materials, sharing your code, you explain well the results, what you like, how you got there. I have publications in substantive journals, personality psych journals, etc., with Bayesian statistics, and it was not a problem. If anything, at this stage, I would think that sometimes substantive journals like it because they recognize the merits of it, and there aren't so many people yet who are using it.
So I have a question about JASP. When you were looking at the regression models, so you had this 64 regression models, and the prior that was used is basically, okay, every model has an equal probability, right? And let's say that from whatever research or background or scientific knowledge that someone thought, okay, this particular feature should be in the model, right? And then you want to give a little bit of higher priority, like increase the prior to the models that has that feature in it. Is there a way that you can do it in JASP, or basically?
I think so. In the prior settings, they should allow for that, or they say somewhere that in the advanced options.
Oh, maybe the WLS weights or something, right? No, yeah, maybe. Because weighted least square weights would.
Yeah, or maybe if you add it to the norm model in the model options, then it's.
Oh, I did not see that. Okay, all right. If you scroll down, there's options that says, okay.
Yeah. Yeah.
The other question that I have, this also might be a little bit of simple one. So when you were interpreting the outputs for the regression part, the base factors that you had was basically comparing to the best model, right? And if you look at it very, very carefully, it becomes obvious because the base factor of the best model is 1, and then you have those. But is there like a guidance that someone can use, and like what are the terms that you're looking at, like what each output is saying?
Yeah, it's the same in a way. Like above 3, there is like a lot of evidence, and you can see that the first 2 models, they're both doing great.
Right.
So yeah, so it's hard to decide. But then, when you get to the regression coefficient estimate, then both will have like not exactly equal, but like a lot of weights into saying what the regression coefficient is. And you could compare them to the newer model too. I don't know whether you saw it, like there's an order option. So now I'm comparing it with the base factor to the best model, comparing it to a newer model.
Yeah, okay, yeah.
Yeah, so there's not much difference between the first 2 models.
All right, so I mean, we're running out of time, but one question I think is, any suggestions for fun JASP modules, super fun and intuitive workshop?
Yeah, thank you. So I really like the learn-based module. It helps you a lot with these graphical representations of different concepts of probability. That's new. I don't think that any other statistical software packages would have anything like that. So it's very unique and new. I would recommend that.
Well, Zita, thank you very much for this wonderful workshop. I had never used JASP, but I think it's very, very cool software. So it's a very cool tool to know about. So thank you very much. And it was a great workshop.
Yeah, thank you so much. And thank you all for coming.
Thank you, everyone. Have a nice evening.
Bye-bye.